thanks to the organizers, Professor Pattanayak and Professor Sunil Kumar, for having me here. And also, it's always great to see students. So I understand this is a course that was on microfabrication. So you have learned a lot of very nice things. I'm sorry, because of other pressing engagement, I could come only today. But I promise that next 3 hours, what I'm going to talk, you are also going to learn something new and very simple, but very important. So what I'm first going to talk is on atomic force microscope. How many of you have heard the name atomic force microscope? Okay, fine. So you already learned something new, a new name. Microscope, all of you know, right? So since you are talking about microfabrication, nano and everything, and ultimately we are all humans, so seeing is believing, therefore we always need a microscope. Why it is called a microscope? Because when it was discovered, seeing 1 micron was considered to be something great. Most of the advanced microscopes these days do not visualize micron. They go pretty much down to nanometers. What is the size of an atom? Inorganic atom, the typical size is about an angstrom. And there are microscopes, high resolution transmission electron microscopes, through which you can see atoms. We have one in IIT Kharagpur. But this is something that is, in fact, very, very interesting in many ways. And how it is interesting, I will tell you. So we all probably know you are a student of a great institute, big institute, where probably you also know that there are microscopes which are beyond optical microscopes, right? You have scanning electron microscope. And here you can see a very nice image of a scanning electron microscope. Some nanoware, hexagonal nanoware, very nice image quality. There is a scale bar over here, which is 100 nanometer. So basically, you are resolving something like 200 nanometer, 300 nanometer. But start thinking what information is missing in this picture. Everything is available. Okay, so before I move on, let me also tell you a brief idea or give you a real life idea of how small we are talking about. So one such thing is, let us talk about human hair. So what is the typical diameter of human hair? Depending on whether you use good quality parachute kesh kala or whatever, right, your human hair will be roughly between 50 to 70 micron, right? So basically, if you are talking about 1 micron, you are 1/50th the diameter of human hair, and 1 nanometer is 1,000th of that, right? And on the other hand, 1 atom is about 1 angstrom, so 1 nanometer is 10 atoms. That is what we are talking about. So moving on, if you just see these 2 images, they are called line gratings. I am not very sure, you might have heard about them. Again, I am asking the same question. Whatever you see, do you think the picture is complete? So when you say no, you are basically reading my mind and giving an answer that no. Where is it incomplete? See, if I take out my cell phone and take a picture of all of you, I will be able to visualize that you are sitting closer and you are sitting at a far distance. But don't forget, a picture is always a 2D projection of a 3D space. And therefore, everything comes at a cost. So since it's a projection, the third dimension, information about the third dimension is missing. And that is precisely what is happening in both of these microscope images. So the ground reality is they are actually different. How they are different? Because now you see, with the help of some instrument, which is this microscope I'm going to talk about, one has height about 150 nanometer, while the other has a height of about 2 micron. But when you just look into any regular microscope, everything will appear to be roughly same, because the information about the third dimension is missing. And therefore, the atomic force microscope, which is in fact a very new instrument, right? It was discovered in 1986, right? And there's a very interesting story. Actually has led to huge advancement in the field of nanotechnology, devices, and everything, microfabrication or whatever. Right. So forget about whatever is written. But this is very interesting. What is interesting is these 2 people, Binning and Rohar, they discovered something called scanning tunneling microscope in 1982. Now, I assume that most of you are from engineering background, so probably you do not know about tunneling. I am also a professor of chemical engineering. I also did not know it, so I will give you a very quick brief about what tunneling is. We all know about flow of current through conductors, V equal to IR, we all know. But there is something very interesting. So they discovered in 1982 the scanning tunneling microscope, for which they were given the Nobel Prize in 1986. In the history of Nobel Prize, this is the fastest Nobel Prize that has been given from discovery to giving the prize in 4 years' time. However, these two people, instead of celebrating and giving parties, realized what is the limitation of scanning tunneling microscope, started working harder, and came up with the concept of atomic force microscope in 1986, which is, soon you will realize from my what is going to come up, is far more generic, right? And it has revolutionized the world in a different way. And please also understand that AFM, atomic force microscope, is something that does not actually capture images, which all other microscope does with different type of lenses, right? So this is something completely different. So here is some formal part. So this whole family of microscopes are called SPM, scanning probe microscope, right? Uh, I will not go into the details because my whole idea is not to bombard you with information. But I would like that after 45 or 50 minutes of whatever I talk, you understand something and carry back something. One of my very former close student of my very dear colleague, the present director of IIT Kharagpur, Somnath, is sitting here. So he must be having some memories of some of my talks. And one thing I assure that whoever comes to a classroom goes back with something. So I do not want you to know what is there, but I want you to know how it works. That is the difference. That is going to be very important. So these slides, everything is being recorded. If you want, I can share these, leave these PDF, PPTs also, so you can look into it, and anyone who is interested can go to Wikipedia or internet and learn great things. So I always tell to my students, Wikipedia is a great place to learn. Feel free to go to Wikipedia and find out 101 information, the first level information, that is pretty good. If you want to work on something, you have to probe deeper, read literature papers, etc., etc. So two things we are going to talk about. One is the scanning tunneling microscope, because this is the fundamental basis. So maybe 10 minutes we will spend on that. And then we will move on to atomic force microscope. But there are a whole lot of other things that can be done with the same platform. So I will just touch upon the glimpses, but not go into the depth. So here is the whole concept of scanning tunneling microscope, which is based on the concept of tunneling current. So it might be something new for you, but it turns out that if you take a very sharp metallic tip very close to another metallic surface, right, both are conductors, and apply a bias, that is apply a voltage, there is a flow of current. So this is something new, because we always know that electrons flow or current flows through a conducting wire. But this is a quantum tunneling effect. You can check it out. So if you actually take a very sharp tip close to a very sharp metallic close to another metallic surface and apply current, there is a flow of current. Apply voltage, there is a flow of current. Of course, where is this current flowing or electrons flowing? They're flowing through the gap, right? So if there are air molecules, they will collide and they will get scattered. So you need all sorts of paraphernalia, you need very high vacuum. And without remembering any formula, just one thing let me tell you, the magnitude of the current is a function of the tip surface separation distance. So in very simple terms, if it is closer, for the same voltage, the current will be higher. If it is further away, current will be lower. Go very far away, no current. Come in contact, it now gets converted to short circuiting and basically transport by conduction. So how this concept can be useful? So just imagine that if you have a surface, right, and if you can move the tip over the surface, so of course you have to understand the roughness is the exaggerated picture. So if you just move the tip at the same level, here you can see the tip surface separation distance is higher. When the tip comes here the tip surface separation distance is lower. So I think there is no need for me to tell you now what is going to happen. At every point, the value of the tunneling current is going to be different. And if you now back calculate the distance for which you get that value of tunneling current, you can sort of mathematically recreate the contour of the surface, right? Considering this to be a datum. Well, this is very simple, right? Very simple concept, but in the process, what you have learned is what is known as the constant height mode of STM, right? So the whole idea is that you have a surface with moderate roughness, you move a tip along a constant horizontal plane, calculate at every point how the value of tunneling current changes, and you reconstruct the surface. What is the problem? Problem is the problems I told. If the tip surface separation distance become too high, current drops to zero. And if you do not know from where you are starting, suppose this is too high and it collides, then the whole thing is gone, right? There is a short circuit, the tip is lost. So can we improve upon this? And the whole idea eventually led to addition of a feedback controller. You all know feedback controller, right? The basic idea. For example, water geyser. So you turn on, you see the light is on. Then after some time, you see it has attained the cutoff. What does it mean? So whatever is the set point temperature, 45 degree or whatever, when the coil has become hotter than that, the power supply is switched off. Temperature is allowed to drop. When it again drops below, let's say 44, again it's turned on. Very simple thing. So if you now add a feedback control, so the whole idea is that, let's say at point 1, when you start, your separation distance is d1. Corresponding to that, you get a magnitude of the tunneling current. Basically, you do not know d1. You calculate, you know the value of IT1, right? From there, you can back calculate d1. Now you move to the second point, right? Where now you know from the figure, it is actually closer. Therefore, the magnitude of the tunneling current is going to increase, right? So what you can easily do, you can compare by how much the tunneling current has increased from point 1 to point 2, right? So here, the way I have drawn the picture, the second point is closer to the surface, therefore tunneling current will increase. Had the second point been lower, the tunneling current would have reduced. But anyway, you could have generated a variation, a difference, or an error, right? So simply feed that error to a feedback loop and accordingly make the tip move up and down, right? So what you can do, you can again take the tip for this, for the context of this particular picture, you can make the tip move upward, right? So that you get back the same value of tunneling current. Is it clear to all? So basically, earlier we just moved from one point to the other point and measured the tunneling current. Here what we are doing, the movement is followed by an upward or downward adjustment, right? And based on what this adjustment is done, so that it is back to the set point value. And can you imagine or guess which actually governs this upward and downward movement? In fact, what professor was talking in the previous lecture, it's a piezoelectric material. This tip is mounted on a piezoelectric material. So basically this error current or error current you feed to the piezoelectric material. Now you know that a piezoelectric material, if there is a current is applied, it changes its dimension. So it might go up or down. It may become fat, short, or thin, long, and it basically moves up and down. So if you now simply track the motion of the tip, what are you getting? You are actually getting the contour of the surface. Isn't it like a tracing paper, right? Basically, when you used to trace the outline of India, for example, or any map, you were not actually moving your pencil on the map, but you were moving the pencil over the tracing paper, tracking the contour. And when you detach, you get a copy of that. Exactly the same thing is happening over here. But any limitation? The limitation is we are relying on the value of tunneling current. And what did I say about the requirement of tunneling current? Tunneling current or tunneling happens between a metallic tip and a metallic surface. So this beautiful technique, what is the beauty of this technique? It is actually digitally recreating the contour of a surface, right? So you know how much the surface at a particular location, how much higher or lower the features are, which otherwise in a microscope, you will capture some image and based on the contrast, our perception that anything that is brighter is closer to us, anything that is darker is below, we sort of create a mental map. I will just repeat a bit and go back here in this particular image. So when you see these features, you have a feeling that some rod or something is up, and probably there is a hole or something, right? This is what all of you feel. Why do you feel that? Because you see these white areas, they are brighter. So you have a feeling that they are closer to us. Something that is dark, we feel that it is further away from us. This is the basic perception. And as I repeat, we do not know how high this is as compared to this. We have a clear idea about the lateral dimension. This is 100 nanometers, so we know this is probably 250 nanometer. This is probably 100 nanometer. But how high or low these rods are, we do not know. But this very simple thing, which is not simple actually, what I talked about, with that, if you now trace the surface in a digital way, you now actually know how high or low they are. So you are already getting information about the third dimension, which was otherwise lost in a regular microscope. But then what is the problem? Problem is this whole thing is actually limited only for conducting surfaces. And there are a large number of non-conducting surfaces like ceramics, polymers, etc., etc. The inventors realized, thankfully, that this such a beautiful and powerful technique cannot be used for these type of non-metallic materials. So therefore, they started to think, if anything can be done to discover or develop something similar, right, which works for non-metallic material. So what is the crux? The crux of the whole requirement is this tunneling current. So basically there was a value of tunneling current around which there was a change, transition. So you had to find out something that replaces the tunneling current. Now tunneling current is easy. It's actually current, so you have a picometer and you can measure the value of it. So what can be that something that replaces tunneling current? So do you know about any force that is universal? So the answer to that is intermolecular interaction, or what we loosely call as van der Waals force. Because you all know about van der Waals force, I hope. So basically it is the simplest, in the simplest form, it is the induced dipole force. So basically, if you remember your school days when you first time learned the concept of atomic structure, you all learned there is a nucleus at the center and electrons surrounding it. You drew nice pictures of electrons nicely separated. Probably your teacher also told you, see, this is partially similar to the solar system and also slightly different from the solar system, because on the same orbit you have multiple electrons, etc., etc. But ground reality is things are not so static and beautiful. So the electrons are basically undergoing a very high frequency oscillation or high frequency rotation, not oscillation, around the nucleus, right? So as a consequence of that, at any given instance of time, the electron cloud around the nucleus is not perfectly evenly distributed. So there is a localization of some charge, which leads to what is known as temporary dipole. This is something you have all studied in your higher secondary level. This is for all type of material, irrespective of whether they have polarity or not. If your structure of the material has polarity in the form of lone pair or something like that, then you have additional interaction, polar interaction, the most classical example of which is hydrogen bond in water. But even if for apolar material, so because of this localization of this temporary dipole, what it does, it induces a dipole of opposite charge. So this delta minus induces a dipole of delta plus on the neighboring atom. And as a consequence, at any instance of time, there is actually a net attraction between adjacent molecules or atoms, which is the intermolecular interaction. And just to tell it, this is a function of the separation distance, 1 by r to the power 6. This is not a function of gravity. So if you remember, when human beings went to the moon, they could jump 6 times, but they did not dilate 6 times, right? Nothing dilated 6 times. Everything was intact. Why this happened? Because how much you can jump or move, we can jump, move, or walk because of the reaction forces, and it's all dominated by gravity. So the value of G on Earth, on Moon, is 1/6 of that on Earth. Therefore, they could jump 6 times. But luckily, interaction force is independent of gravity, and therefore there was no distortion either to their body or to their spacecraft. So this van der Waals interaction is universal. So the whole idea now changed to, if we can again bring in a tip and now can do something to track the van der Waals interaction between the tip and the surface instead of tunneling current, then probably this technique can be used for all type of material. This is the basic philosophy behind the development of AFM, right? Atomic force microscope. Now, why this word atomic force? Because this van der Waals force, based on which this microscope works, originates because of interatomic interaction. Therefore, the word atomic force microscope. This has nothing to do with nuclear reaction, which typically atomic energy, for example, refers to, right? So, conceptually this is fine. This is something you will learn this in next 15 minutes, and you will all understand. This is the basic hardware setup of an atomic force microscope. This is also very interesting. And since my previous speaker actually talked about piezoelectric material, that actually makes my work easy, because you see here, you already see the word piezoelectric scanner. So this tip, as I mentioned, for that STM, here also you need to, it is actually mounted on a piezoelectric scanner. But there is only one problem that happens, that arises out. Probably I'm not going to ask you what is the problem, because in a regular class I would probably teach it in a little slower fashion so that you grasp the concept even better. The problem is as follows. When in case of tunneling, scanning tunneling microscope, you were basically measuring the tunneling current. And you all know, to measure current, you basically need an ammeter. Basically, the magnitude of tunneling current is very, very low, so you go for a picoammeter. However, what meter is going to measure the van der Waals force? Turns out there is no such instrument available which can measure the van der Waals force. So some arrangements, some optical arrangements were done to track the change in this force, and that is what I am going to teach you in the next few minutes. This whole arrangement of atomic force microscope, it uses a tip again. The tip is used for a completely different purpose, not for tunneling current anymore. But this atomic force microscope tip, what you can see here, is actually one of the finest examples of micromanufacturing, let me tell you. So this is on some material like a silicon nitride or whatever. What you can see, this tip is not a tip just attached to a piezoelectric scanner like an scanning tunneling microscope, but this tip is mounted on a cantilever. So I guess, being engineering students and mechanical engineering students, you all know about a cantilever, right? So you basically have a micro cantilever like this, and at the tip of the cantilever, at the edge of the cantilever, this tip is attached, right? So why it is done like that? So here is another microscopic image of the AFM tip. These two images are very interesting. They are actually scanning electron microscope image of atomic force microscope tips, just to understand, right? And then here are the other components. You will understand some of them now. You will not understand some of them now. You will understand in few minutes time. So basically, this is the sample whose topography you would like to find out. This is the sample. Here is the tip we already talked about. This tip is mounted on a piezoelectric scanner, right? This is very similar to the scanning tunneling microscope. We talked about a feedback loop there in the second mode, you remember? So here also we have a feedback loop. But these three, then everything is interfaced with the computer, so that is nothing very important or major. But these three things, a laser source and a position sensitive photodetector or a quadrant photodiode, is something that is new in this atomic force microscope. And these hardwares are basically introduced to circumvent the problem that you cannot measure van der Waals force directly. So this is, and you will understand in next few minutes how it works. So basically, these are the major components of the AFM. Let me see if I have a picture of an AFM. I'm not very sure. So all these we will run through. So this is the picture of an atomic force microscope, right? In my lab in IIT Kharagpur, we have a microscope looking like this. But don't get carried away. So this is actually a lens. Don't get carried away by the fact that that is the microscope. That is actually an optical microscope. It is not the atomic force microscope. Atomic force microscope is very compact, a small device like this. Does not look like a microscope. So I don't know how good the resolution of the image is. This is actually the atomic force microscope. This one is the atomic force microscope, only this part. Everything else, because we actually use our eyes for understanding everything, whatever we are doing. So generally, atomic force microscopes are installed below a low resolution optical microscope. So many times I ask the students, bring them to the lab, show them, see, this is the atomic force microscope. Where is the microscope? And invariably the answer I get is this is the microscope. This is not the microscope. This is actually the microscope. And you will realize, if you are following me, something I told already, that unlike other microscopes, which all take pictures of some form or the other, an atomic force microscope does not take a picture. It does something completely different. And you will understand what it does. So we talked about these things. Now, before I explain this slide, I will just spend a minute on the tip that I was talking about. So this is basically the arrangement. So you have a cantilever to which the atomic force microscope tip is attached, and just a small additional microfabrication feature on the opposite side of the cantilever, you have a shining area which actually acts as a mirror, right? So you will understand why it happens. So let's go back to one component that we were talking about. This is this quadrant photodiode or position photodiode. So what exactly is this photodiode? Probably from the word itself, you will have some idea. So if you shine light on that, some voltage will get generated. This is a very simple thing, photodiode. What the word quadrant reminds you of what? A graph paper. So basically, this is such a interesting photodiode, again a marvel of microfabrication, that the diode is actually split up into 4 parts, and the parts are first quadrant, second quadrant, third quadrant, and fourth quadrant, right? So you know, plus plus, minus minus, whatever whatever. So basically what it means, that for a diode, if you shine the light, and in this case the light is actually laser light, at the center the reading is 0. Further away you go from the center, the value of the current starts to increase. And since it's a position sensitive diode or a quadrant photodiode, it actually can understand or can read or detect where the light is falling. So let's say if it is falling here, it not only tells you the actual value of the current, right, or the voltage, but it also tells you what is the value of the x quadrant and y quadrant. So this way you can independently, so probably you can all understand that this is 0 millivolt, and any concentric circle is actually locus of some unique value. Let's say 1 millivolt, 2 millivolt, you will basically get concentric circles. So let's say if you have a hypothetical circle over here, right? So any point on the circle, the value of the voltage will be same, but at different points, the quadrants will be different. The x and y, the ordinate and abscissa will be different, and that can be read here, right? So this is one very important part, the photodiode. And now what we do, we basically now have 3 different hardware components. We have a laser source, exactly like this one, a smaller diameter laser. We have a photodiode somewhere, and we have a cantilever, right? And what we have to do, we basically, so the modern instruments actually do this coupling, what I'm going to talk about automatically. but old-time users like me, I can still operate an atomic force microscope. We prefer to do it manually because that gives you a very good feel about how good your microscope is going to work. So basically, you have two sets of orthogonal vernier caliper screws, nothing else. So you can rotate these two screws to make movement, your simple dynamics lesson, right? They move in such a way so that, so as I told, there is a reflecting coating over here. So basically, you move the screws in such a way so that the tip basically comes in the path of the laser light. So suppose I am shining this laser, right? And if I now bring in something in the path of the laser, firstly, you see that the laser is no longer falling at the floor. And secondly, instead of this cell phone, if I now have a shining mirror, the light will start to reflect from here. You remember that I told there is a shining area, micro mirror over here, so which you bring in the path. So what is the consequence? Now the laser starts to reflect, right? And now what you do? You now turn your attention to this photodiode. Again, two sets of screws. You rotate them left, right, aage, piche, upar, niche, whatever you feel like. And you rotate them in such a way so that now you bring in this photodiode in the path, not only the photodiode, but the center of the photodiode in the path of the reflected laser light. And what is the reading? Reading is, as we already talked, since it's falling at the center, reading is 0 millivolt, right? What you learned, you sit in the microscope, in half an hour you will learn this process. But this is the process of alignment of an atomic force microscope. What are you doing? Three completely separate hardware elements, the laser source, the tip, and the photodiode, you are optically coupling, right? But why are we doing all these things? We are doing all these things to get an idea about the surface, about the sample, right? But here, the sample is nowhere in the picture. Yes, that is basically the case. So what needs to be done? Next thing that needs to be done is this whole thing needs to be brought close to the sample, because you remember in the tunneling thing, it was close. Here also the same thing needs to be done. So here, now you see that you basically, now if you look at this picture, you can already say what this is. You basically have an aligned atomic force microscope, right? The alignment has taken place. But here is your sample, which is far away. So what you do now? You basically try to bring the sample or the tip close to each other. And how do you do it? You basically use a motor. You basically use a stepper motor, which has very low resolution, and you are from mechanical engineering, so you know very well how a stepper motor works. So you basically, these two are separate. Either you move this downward or you move this upward with the help of a motor so that the relative separation distance reduces. Fair enough. Now, when they initially, so if you compare these two pictures, 1 and 2, what is the difference? There is no difference in the arrangement of this because they are being manipulated manually by moving the screws here and there. And only thing you can see is what you are doing. The separation distance reduces, right? But when they come even closer, what happens? What happens is you now have to recall the concept of van der Waals interaction. So when two atoms or molecules come close to each other, there is an interaction. Similarly, when two surfaces come close to each other, in fact, if you are also there in the afternoon lecture, I will show some nice videos on this. When two surfaces come close to each other, there is also this van der Waals interaction. So when do these surfaces come close to each other? Every time you clap, every time you put your hand somewhere, every time you put an object on another thing, this is happening. Now these are rigid objects, so there is no signature of these interactions that are visible. But now you understand why we have taken on a cantilever. Since it's a cantilever, so it has to be, in order to be a good atomic force microscope tip, it should be, so its stiffness should be such so that it is sensitive to these tiny forces. And that is again a micro manufacturing wonder, right? So now what happens? Now as the tip and the surface starts coming close to each other, there is now an attraction between the tip and the surface due to the collective effort of the van der Waals attraction of all molecules. and consequently the tip now bends, right? And eventually they come in contact, but we call it the jump to contact. So basically, anyway, because of the motor, the tip and the surface would have come to contact, right? But what is happening just ahead of contact, the tip is experiencing an additional force and it stoops consequently and therefore comes to contact earlier. I'll give you a very silly example. So in Indian culture, we have this, in India, we have the culture of touching somebody's feet, right? So what do you have to do? You have to stoop. Let's say as you start to stoop for touching somebody's feet, the person also raises his feet. So what you have to do? You have to stoop less. That's exactly something similar that is happening. We call it, it's a beautiful phenomena of physics. We call it jump to contact, right? So basically contact has been established. But we do not stop here. We actually allow the tip to be pressed a little more. So what happens now? So if after establishment of the contact, this movement of the motor is continued, so it is basically, it will be pushed a little upward. Of course, the forces are very, very gentle. This is done for some specific reason, which will become clear to you in next 5 minutes time. And then, if you have been following my whatever I am telling, photodetector, now we understand. Why the laser light is falling at the center, now we understand.
That is step 2. Which one is moving?
I mean, the way I have drawn is the whole thing is moving, but sir, it can be anything. In fact, there are atomic force microscopes. So,
my worry is you have centered it at the point, so that gets displaced.
No, so if this whole paraphernalia moves or whatever, then the whole assembly moves.
Yeah, okay.
So there is no relative displacement between the two. Right. So just a quick point. So if you are following whatever, you also saw there is a small green colored spot over here, which I did not explain, and I did not explain it deliberately. What is that? That is actually the set point. And who chooses the set point? It is your prerogative. So typically, the photodiodes have a range of 0 to 10 millivolt. So you can choose whether you would like to scan at 3 millivolt or you can scan at 4 millivolt or whatever. You choose it. So basically what is now happening, as the tip is experiencing jump to contact, right? Since what sir was telling, there is a movement of the cantilever. So the laser light also gets shifted. It does not fall at the center anymore, it falls somewhere else. And now as you continue to push, as the nature of deflection basically changes from attractive to repulsive, the laser light also shifts, right? The question to ask is, how long would you allow your motor to continue with this process? Because if you do not intervene and stop somewhere, the moving motor is simply going to rip apart your cantilever. That's what is going to happen. Well, turns out that the program is logicked in such a manner that when the reflected light falls on the set point, the motion of the stepper motor stops, right? And the piezo on which the cantilever is mounted gets activated. So what have we learned? We have learned, but what have we done basically? In the previous step, we had optically coupled the three components of laser source, cantilever, and the photodetector, which was alignment. And here we have physically coupled the aligned cantilever with the sample, which is known as the process of approach. So now life actually becomes quite easy. So you now have an AFM which is ready to scan. So I think these two pictures now make sense to all of you, which 20 minutes back were completely Hebrew to all of you, because now you understand. Here what we are showing is the aligned tip, and here what we are showing is the approach tip, right? And we also understand that after approach, the reflected light does not fall at the center, it falls at somewhere else. And what is causing this deflection from the center? It is because of the presence of the surface, which is basically deflecting the cantilever, and the consequence of that is optically detected on the photodetector, right? So now what you do, so again, these are some cartoons to give you an idea about what is happening. Now what we do is we basically move the tip all over the surface, back and forth. So basically what I explained even in case of an STM was as if it was moving on a line. You do not just limit yourself to a line. So it's basically a set of nested do loops, right? It moves along a line, comes back, goes to the next line, again moves up back and forth, again like that. So it is basically called the fast axis and the slow axis. You can choose in commercial machines whichever you want to do, your fast axis and slow axis. So even a pattern like this is perfectly fine. So now what we are going to the sort of the last thing, uh, we are going to focus our attention as the tip moves from one point to the next point. And that is where all the crux is. Exactly the way we talked about the scanning tunneling microscope, right? If you recall that basically in the constant current mode, the tip moved from the first point to the second point. There was a variation in the current. That variation in the current was fed to the for the feedback loop, and consequently the piezo adjusted. So let's see, here is some detail, we can skip about it. So basically here we have the point 1. Now let's say this is an exaggerated picture of the sample surface. So it moves to point 2, which is at a higher elevation. So now if it is at a higher elevation, what is going to happen? What is going to happen is the tip is going to deflect even more, right? And again, what is the consequence? The moment the change in the deflection in the tip changes, the light is no longer going to fall, right, at the set point. It is going to fall at somewhere else, right? Why this is happening? Because the intersurface force is changing. We do not measure the force. We have no means to measure the force. But what we can see is an optical consequence of that. And what is the consequence? Since the force changes, now light does not fall at the set point, it falls at somewhere else. Does it satisfy your purpose? The answer is yes, it satisfies your purpose, because the moment light is falling somewhere else, you are actually generating a deviation in voltage. Because where is this? This is not at a random place or a mirror, this is on the surface of a quadrant photodiode. So every time light falls somewhere else, it can read the voltage, and it can also show it's a quadrant photodiode, so what are the values of ordinate and abscissa. So you now get a deviation or an error. So what to do? You simply feed this to the feedback loop, and accordingly, what in this particular case, the way the figure is drawn, now the piezo will expand or compress in such a way so that it goes up, right? So that the deflection becomes equal or identical to this point, right? And again, laser starts to fall at the set point. So if you simply, like the constant current mode, can track the motion of the piezo now, you basically can mathematically reconstruct the contour of the surface. So if I show this now, probably it makes sense to all of you, because what have we shown? That all you are doing is a computer programmed rastering. That is that the tip visits point by point, every point on the surface, and every place as it comes from the previous place, depending on whether it is at a higher elevation or lower elevation, the piezo adjusts itself. Either it goes up or comes down. And all you are tracking is basically, as a function of the spatial coordinates, x and y, the value of z. This is all that what you are tracking. So after you have scanned your region of interest, which can vary from 100 micron by 100 micron down to 1 micron by 1 micron, or 500 nanometer by 500 nanometer, whatever it is, you basically get a data file like this. You do not get, I told you, we do not get a picture, right? We do not get a picture. We actually get a data file like this. And then what do? We do some very simple thing. We actually find out the z range, the minimum value and the maximum value, normalize it between 0 and 1, convert it into a grayscale, and just project it like this. It's basically a contour, 3D contour plot, right? So what is the beauty? Beauty is the lateral scale bar, the x and y you anyway get, right? But you also get this, right? This is where the true dimensions in the vertical directions are. Because here again, if you look into it, this is some sample, I'm not going into the detail, but very nice picture. Here again, if you look into the figure, you will intuitively have a feeling that there are some lines, right? And the black regions, right, are something that is separating a grating structure or something, right? And there are some secondary depositions which have happened due to some reason, which are like micro pillars or nano pillars or whatever. Any microscope would give you this information, but what other microscopes will not give you the information is that the height of the lines or whatever features you have is limited to about 140 nanometer. This is an information that often, in fact, in the next lecture, I will give one example where this information, the information about the vertical dimension, becomes most crucial, and without that information you actually cannot do anything. So this is what is the beauty of the atomic force microscope. Since it basically depends on variation in the intersurface forces, it does not measure tunneling current anymore. Therefore, it can be totally useful for different all type of material. In fact, today, in today's world, AFM is 25 times more popular and maybe 50 times more popular and well utilized than the STM. I feel that this pair of people, the group of people, these two people, should have been given another Nobel Prize for the discovery of atomic force microscope. They got their Nobel Prize for discovery of the scanning tunneling microscope in 1986, and the same year, the concept of atomic force microscope was also discovered. Right? So this is how basically it works, and what we learned is the concept of contact mode AFM. So basically, the tip is in contact, you run it back and forth, and I will just take 2-3 more minutes. We are also running out of time, and you get this information. But if you feel that you are actually dragging something back and forth, there are two possibilities. In your childhood, you have all used pencils. So when you use a pencil for longer duration of time, two things can happen. Number one is the pencil becomes blunt, right? The other thing is, if you apply, I'm sure some of you, at least I had these catastrophes, if you apply too much force, sometimes with a pencil you have pierced the paper. Same thing. If the surface is soft here and you drag a tip over it, so basically what happens is that there is a possibility that the sample itself gets damaged because of the rastering motion. So this was particularly pronounced for polymeric material or soft material, right? So what additional thing people came up with is, don't forget, the tip is mounted on a cantilever, which can behave as a spring, right? So you have an additional drive motor. Basically what you do, you find out the natural frequency of the spring and you oscillate it there. So as you oscillate, I will not go into the details. This is what is known as the intermittent contact mode. So basically what you do, the tip is now mounted on a cantilever which is oscillating. And as the tip comes now closer to the surface, the cantilever, the tip sort of starts knocking the surface. It's exactly like how blind people walk with a stick, right? And from there, the popular name of this mode is called the tapping mode. So basically, you do a tuck, 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 and then if there is a stairs or something, is basically oscillating with the same amplitude, and he finds, oh, it's not touching, so there must be something at the lower level. And it is basically this concept that is now used very widely. It is known as the intermittent contact mode. In one lecture, I do not want to go that much into detail because then everything will get mixed up. So the advantage is that here are different modes or whatever. The advantage in very simple terms is you are no longer dragging a tip over the surface. So the possibility of tip mediated damage is reduced now, but you are gathering again the information with the help of the photodiode. Basically now what you measure is how much the amplitude of the oscillation changes if you have a higher or lower feature. So it is oscillating with a particular amplitude. If you now have an obstruction, the amplitude gets reduced. If it is lower, the amplitude gets increased, and basically you map that again to the feedback loop. And this is what is known as intermittent contact mode. So these we now know. These are AFM probes. In fact, SEM images of AFM probes. They are very sharp because it is basically the tip now travels from point to point, And now you should understand the so-called, there is no resolution, optical resolution here, but can you measure, let's say, 10 micron with your regular diagonal scale? The answer is no, because you have a least count of 1 millimeter. So if your tip itself is 50 nanometer wide, the minimum lateral dimension you will get is also 50 nanometers. So typically, AFM tips are not as sharp as STM tips, but still they are quite sharp so that it can gather information. And these pictures I have shown. So this is sort of something I will not touch upon. So there are a whole lot of additional analysis that can be done with the AFM, because remember, unlike other microscopes which actually take a picture whether some electron is getting reflected or electron is passing through it, here a tip is actually going and physically touching the surface. So since the tip is going and physically touching the surface, a whole lot of things can be done with the tip. And these are the advanced modes which are very widely used now, but maybe in some other course I will talk about it. So all these I will skip, but here are some nice images I would like all of you to enjoy. So these are some fibers, for example, the AFM images. All right, so some mesh that has happened. And now, as a knowledgeable kids now, whichever class I teach, I always tell them, you are knowledgeable folks. So you are also knowledgeable folks now. So if somebody shows you an AFM picture which is only limited to this, immediately point out, this is missing and I don't accept. Because otherwise, whatever you see on the left side, it is a major part of the picture, but that any microscope will give you. It is only this part that atomic force microscope only can give and nothing else can give. I hope you all understand the vertical scale bar. Right, so here are some membranes. So these are the rose petals under the atomic force microscope, very beautiful features. Yellow rose petal, a cluster of micrococcus bacteria. So these are again bacteria, so they are very soft living cells, and with this tapping mode they do not get distorted and you can image them. Some sort of cancer cell probably. Here again a cluster of cells, and in fact what you see here, if you recall your 7th or 8th standard biology, here is the cell membrane, here is the nucleus, and everything you can visualize with the microscope. And yeah, here you can again see, I think this is a nervous system cell, and you can see the cytoplasm and nucleus, spherical nucleus. I don't know whether I have the picture, but one picture we generated in our lab where we could also clearly see the mitochondria, some fibroblast cell, etc., etc. Yeah, so basically that's all what I wanted to teach you. I hope you have learned something rather than the fact that atomic force microscope, there is of course an instrument, and you now understand it's a very interesting type of a microscope which does not capture a picture but actually captures some data, and with which you do not lose the information about the third dimension which you otherwise lose in any microscope or any picture, right? So next time onwards when you take a picture with your cell phone, right, you remember that it's a nice picture. All the cell phones, let me take one, it's a nice picture with all high resolution cameras, but it comes at a cost of loss in the information of the third dimension because of the projection. So with that, I'll stop here. Thank you very much. Right. Yeah, sir. So I'm done. I don't think anybody will ask a question before lunch.
Sir, can you just show that bacteria? And one cytoplasm, I think you have shown. No? So you told tapping occurs. So tapping doesn't kill the bacteria. Or
no, so these are not living cell images. They are killed. They are dead. So, but you have to.
Cytoplasm also. They are not disturbed.
So they are like no. So you can in fact do experiments where, so you know, cell membranes of healthy cells and disease cells, they have different strength. So you can also sort of enhance the force of this tip, and you can in situ rupture them. So all sorts of very advanced things can be done, but which I did not want to discuss.
What is the cost of this microscope?
It's much cheaper as compared to your HRTM or something like that. It is like in INR, it's about a crore. You get a pretty good AFM. But operating an AFM is little tough because a tip actually goes right. In fact, we did some very interesting project for 3M or some company. I should not take names. So you know about the sellotape, right?
Yeah.
They wanted to see the morphology. So normally, when you take the tip, AFM morphology, because it's an adhesive tape, the tip was getting attaching, right? So we could cleverly use the tapping mode so that it went, picked up the morphology, but did not attach. Same thing. I mean, so the person who does it for me, I have trained somebody, not my student. We have an operator. So basically, to get your question, so I'll just tell you. So your question is very well taken. So basically, you need to have a clear idea. Remember, the students you were listening, I told what force you are going to choose is your prerogative. That is the crux. So depending on the nature of the sample, with how much force you want to scan, you can basically destroy your sample or kill your sample or rupture your sample or whatever. So that is something which comes with experience, etc.
So thank you.
Thank you very much.